Wonderful. It's great to be here. Thank you so much, Hervé and Moshe, for asking me to give this talk. It's really nice to look out at the audience here because so many of the people here have been interns and postdocs and permanent members and sabbatical visitors in my lab, so it really feels like old home week being here. So I decided that I'm going to talk about Graphons, which is something that Christian and I have been doing for over a dozen years now. It's a very long title, but I get from people in economics and in AGT, what are these Graphon things? And, can we use them? Should we be using them? So, since we started doing this, there are thousands of pages worth of papers on the subject, and the two of us already have about 800 pages of papers on the subject, so there's a lot. I'm going to go through it quickly, but I'll try to give you some flavor for why we did this and where you might want to use it. Okay, so I'll start with motivating questions. Then I will tell you how to get a graphon from a sequence of graphs or networks. I'm thinking of applications of networks. Then I will tell you how, given this function, you could generate models of graphs more interesting than just, the Erdős-Rényi random graph, which doesn't describe most real-world networks, and then how to actually learn, how to machine learn the network from the data. And finally, I'll mention one application of this that we've done recently to trying to figure out something useful on a network. Okay, so every place we look, we see networks. Many of them are networks that people here care about, certainly social networks. People here care about a lot. There are economic networks, many, many networks. Okay, so three related problems. What Christian and I, with László Lovász, Vera Sós, and Kadi Vestergambi, started thinking about years ago, 12, 14 years ago, a long time ago, is what is the correct notion of a limit of graphs? And of course, if you make your notion really strong, everything converges to the same point. If you make your notion really weak, everything converges to a different point. So what we wanted was a notion that was meaningful, that contained enough of the information, but not too much of the information. Then the next question is, how do I non-parametrically model real-world networks? And how do I estimate or learn this non-parametric representation? And then finally, some applications. For example, one that I'll talk about is if I have a very sparse and, in fact, noisy sample of a denser underlying network, how do I predict the unobserved properties of the network? So for example, on the Netflix network, how do I estimate the probability that a given person will like a given movie? Or some of my economist colleagues have told me that they are interested in how they complete a social network which has been very, very sparsely sampled. What's a statistically good way of completing the network? Okay, so similarity of networks. So here's a picture of a brain cell and the universe, and they look eerily similar. And so this is how we started thinking about it over a dozen years ago. By analogy, so I come from physics, by analogy to a thermodynamic limit of a statistical physics system, or differential equations as the limit of interacting particle systems. And both of these are very, very useful. They contain a lot of information on the limit, but not so much that you can't see the forest for the trees. Is there a meaningful way to compare large networks and define a limiting network? Okay. The second question, modeling and machine learning of networks. So we see a picture of Facebook, we see a picture of LinkedIn. So how can I take a single snapshot of a really large network today and learn the network? For example, to predict what it will look like when it's twice as big, or to predict really a non-parametric network model, because if you keep on insisting on having parametric network models, you end up overfitting as the network grows and grows. So I want to do this to do A/B testing or collaborative filtering, for example. And the short answer is that I get an estimate of the graph limit which describes that network today. So I say to you, this is the function that best describes Facebook, or this is the function that best describes LinkedIn, and I use that estimate to predict what it will look like when it's, for example, twice its size. And in a work which we completed a few years ago, but the review process in statistics seems to take forever, this gives a consistent estimation for massive networks, okay, a statistically consistent estimation. Okay, finally, how do I infer missing entries in a sparse network? And the last theorem that I'll show you is that we can efficiently estimate these missing entries from very sparse and very noisy data, much sparser than the previous results, and in a regime where it is realistic to actually start to do so. Okay, so networks to me are graphs. They have vertices and they have edges. And so there's an adjacency matrix with ones and zeros. One if there's an edge from I to J, it's a symmetric matrix, and zero otherwise. And then I've got these things called graphons that in general live on sigma finite measure spaces. And I've got a function, W, on this cross product of the feature space, which is an analog of the adjacency matrix here. And that will tell me it will tell me the probability, for example, that I is connected to J, okay? And it will be based on the underlying features. So here I may have the things on which we are connecting. It could be a vector which describes, you know, IQ and height and income and all kinds of things. Okay, those are the features, and then given those features, what are the probability that we connect to each other? Okay, so I get from this adjacency matrix of ones and zeros to some function. Given that function, you know, you walk into LinkedIn and I tell you, great, here's the function that describes LinkedIn, okay? Now you say, how can I generate random graphs which are consistent with LinkedIn? And then, do I get a consistent estimation out of it? Can I prove to you that? So what happened to us was about 3 or 4 years ago, we went to NIPS, and we had been like off in math land for 10 years, like just proving all these theorems. And then we found all these people who were actually using the Graphons to model their real world networks and fitting them. And we said, oh, that's really nice. But in the case of non-dense graphs, can you prove that it's statistically consistent? And there was nothing there, so that's what we landed up doing for the last few years and other kinds of sparse graphs. Okay, so let me give you the heuristics of a graph limit, just a picture. Okay, so I'm going to take the adjacency matrix of a graph, and I'm going to say, so let's just look at one graph, the half graph, and I'm going to say that if I connects to J, then I'm going to color in the block. So if I have a 1, I'm going to color it in, and if I have a 0, I'm not going to color it in. And then I'm just going to take this thing that looks like a limit of that picture. Okay, if I did this with the Erdős-Rényi random graph with p equals 1/2, I'd get this kind of modeled thing, which when I took the limit would just be a function of height 1/2, which is the probability that a site is connected to another site. But what about permutations of vertices? I mean, these two things are the same thing with vertices relabeled. And we all know that, graphs only make sense up to relabelings. Well, there's a much bigger degeneracy for the graphon with Lotzi, Lovaas, Christian, and I, and so the B is always Christian. With Lotzi, Lovaas, we proved that this function is unique up to measure preserving bijections, okay? So it's there's a large degeneracy there. Okay, so here are a few more examples. If I take a randomly grown, dense, uniform attachment graph and order it by degree, it turns out to converge to the function 1 minus the max of x and y, which is 0 or 1, okay? So this is a bounded function. If I do this with a preferential attachment graph, a dense one, I get log x, log y. So you'll notice that this function is unbounded. And you can't really see it, but it gets very, very black here, okay? Because we have unbounded degrees. Okay, so now, how do we try to make any of this precise, okay? So I'm first gonna talk about dense graphs and metric convergence for dense graphs. So what I wanna do is I wanna take two different dense graphs and I wanna ask, are they similar to each other? How do I compare them, okay? And then they're probably not even the same size. So here's what I'm gonna do. I'm gonna take the, I'm first gonna tell you what a Fries-Kahnen cut norm of the adjacency matrix is. So just for one given graph, what the Fries-Kahnen cut norm says is, let me take the biggest cut in my graph. Okay, so I can think of T as the complement of S, try to pull my graph apart so that I'm cutting the largest number of edges. That's the Fries-Kahnen norm of the graph. Now what I'm gonna do, if I have a graph of size 13 and a graph of size 17, I'm gonna take every node of the graph of size 13 and blow up each node 17 times and put in a complete bipartite graph in there. I'm gonna go to the one that's 17, I'm gonna blow up each one 13 times, put a complete bipartite graph in there. I'm gonna take the difference of these two blown up graphs, which are now the same size, they're each 13 times 17, and I'm gonna take the cut norm of that. So this is somehow telling me I scale them to the same size, I look at what the biggest cut is in this difference of the two graphs. And then of course I only only care about things up to relabelings, so I'll minimize overall the relabelings of the points. And I'm gonna call that the cut metric between the two graphs. And so once I have a metric, I can say, okay, well, what if a sequence of graphs is Cauchy in that metric, okay? Is Cauchy convergent in that metric? Well, that's what I call metric convergence. And Lotzi and Balazs-Szegedy proved there actually was a limit here. I mean, it's a martingale convergence argument for this Cauchy convergence, okay? And for dense graphs. And so I'm gonna call this limit a graphon, but it's like those pictures you saw, but there's a large equivalence class because it's up to measure preserving bijections. Okay, so now here's and just remember, we could have defined a notion so that everything went to the same point or everything went to a different point. So why do I think Cauchy in this metric is a good notion? Okay, well for a dense graph, I can talk about subgraph convergence. So don't read that, just think, what would it mean if the edge density converged, and the triangle density converged, and the four-cycle density converged, and the Peterson graph density converged, and all finite graph densities converged? Then I would say it's subgraph convergent, okay? All finite subgraphs going along my sequence of graphs, you know, Facebook today, Facebook tomorrow, Facebook the next day, all of those converge. Facebook is not a dense graph, but let's just say that it were. Okay, so for dense graphs, it turns out that subgraph convergence is the same as metric convergence. So these two things which seem a priori so different, this Cauchy and this thing where I'm taking the cuts versus all subgraphs converging are the same thing for a dense graph. And this is why the combinatorialists just loved it, because they do all kinds of things on subgraphs, okay? And here now they can just look at this limiting graph and know that all the subgraphs converge. But Christian and I, being statistical physicists by training, were like, no, we want other notions. Okay. So we came up with, over the years, lots of different notions. In fact, with Lotzi Kadi, and Vera, we came up with the first three notions in addition to subgraph and metric. So the first one is microcanonical free energy. So I put free energies on my graph. Okay, so any points that are connected have some energy in between them. And I call it microcanonical because I fix the ratio of the number of red sites to the number of blue sites to the number of green sites, and I have energies that say maybe a red site interacts with a blue site with this probability and that, or this energy and that energy. So the convergence of these free energies sounds very different. Computer science, I can ask for the convergence of all max cut and min bisections of my graph. I can ask for all multi-way cuts and bisections, so combinations of cuts and bisections. So these are sounding very global, right? Because cuts and bisections are big things. Combinatorially, I can mod out the Semirati partitions of the graphs. And then with David Gamarnik a few years later, we came up with a large deviations rate, which corresponds to entropies. So I not only hold the vertex densities fixed, but I also hold some edge densities fixed and then get a large deviations rate from that. And what it turns out is that for dense graph sequences, not only are metric and subgraph the same, but all 6 of these notions turn out to be the same. So now you're really starting to think, okay, there's something here, okay? This is a meaningful notion. Okay, now you want to go to sparse graphs. So first, sparse graphs of bounded degrees. So we did this with Lotzi and Jeff Kahn. They're much more complicated. They're much more fragile. Benjamini and Schramm, I don't know, about over 15 years ago, maybe 20 years ago, they came up with a notion of convergence where you fixed the root and then you looked at the convergence of a graph rooted there, okay? So for a sparse graph, like, on ZD or something, turns out that subgraph convergence, so edge, triangle, et cetera, is the same as Benjamini-Schramm convergence. But these are weaker than convergence of free energies and large deviation convergence. So these are strictly weaker. So sparse graphs are very fragile. Sparse graphs of bounded degree. Now what we really care about are sparse graphs of unbounded degree, okay? Preferential attachment graphs and things like that. So Facebook, LinkedIn, all these large graphs are actually sparse graphs of unbounded degree. Okay, well, let me tell you why subgraph, and this is why it took so long. There was a gap of 5 or 6 years in there. And I think it was because people kept holding on to subgraphs because they were so nice. But subgraphs really don't make any sense in this case. So let's think of GNP with P, with the edge density being n to the minus 2/3. Then what, with P being n to the minus 2/3, then what is the edge density? It's n for one endpoint, n for the other endpoint, times n to the minus 2/3 is n to the 4/3, okay? Now let's look at the triangle density. It's n times n times n for the 3 vertices, times n to the minus 2/3, n to the minus 2/3, n to the minus 2/3, so it's n. So I could wipe out every single triangle in my graph and not change my edge density, right? My edge density would still be n to the 4/3, even though I've wiped out every triangle. So obviously, I can't have both the edge density and the triangle density converge, okay? Sparse graphs just are too fragile for that. However, most real-life networks are sparse, but it turns out that the L1 norm of this sequence of graphs is the density of the graph, so it's going to 0, okay? And also many real-life networks have power law degree distributions, so D max over D average is blowing up, whereas it's bounded for dense graphs. So what we want is a theory which works for sparse graph sequences with mild assumptions on the density, like max density or average density. okay? So we actually came up with two very different theories. Let me just give you a definition here quickly. W super GN is the piecewise constant graphon corresponding to the graph G. Okay, so I could write any graph as a graphon just with, you know, so it's a function on 0, 1, right? We saw those black. Okay, so what I'm doing now is I'm taking my graphon and I'm dividing through by the density so that the L1 norm is going to be non-trivial, otherwise the L1 norm would go to 0, so I'm dividing through by the right thing. So what this does is it kind of makes all of these higher, right? Because I'm dividing through by something which is going to be going to 0. And I say that it's convergent if in the natural cut metric, dividing through by this norm, this goes to 0. So this sequence, which I call rescaled, because I've divided through by the density, converges to some function, okay? And this actually, so we did this with Henry Cohn and Yufei Zhao when Yufei was a grad student here, and it leads to generalizations of many of the results for dense sequences, provided that the average degree is tending to infinity, okay? Not like n squared, right? I mean, it's not like the density is going like n squared. It can be much sparser than a dense graph. Okay, and then a couple of years later, working with Nina Holden and Henry Cohn, Nina's also, she's still a grad student here, we came up with a very different notion. We said, what if instead of having this, instead of thinking of this as a function on a bounded interval 0, 1, where I might think of W as the probability that X is connected to Y, what if I stretch things out so that they were in the whole positive quadrant instead of in this 0, 1 square, okay? And what this corresponds to is that your features become unbounded, okay? So I could connect on something that's bounded, or I could say, oh, I'm doing it on wealth, and like we all know, wealth is unbounded, right? And so it's a different limit now, and I stretch, so I put in a square root of this thing, which is going to 0. Oops, well, I guess we know who's online. Okay, I should shut off Skype. So do these notions of convergence give subsequential convergence for anything? And this is why it's hundreds of pages of mathematics. No, the mass can disappear up in this case, or to infinity in the stretch case. And the solution to these problems is that we developed notions of regularity, which we called uniform upper regularity and uniformly regular tails. And we got many of the results, not the subgraph convergence, but many of the results that we got for dense graphs for these other notions, provided that they satisfied that, and as long as the average degree blew up, which is true for most of the graphs that we care about. Okay, so advantages of this first one, this rescaling one, we get power law graphs converging, which is nice. The degree distribution converges. We can estimate it from a single sample. And in fact, I'll mention in a little while, it can be done differentially privately also. So this is the one kind of tie-in with the other plenary lecture, which talked about fairness, which is a notion very similar to differential privacy. The advantage of the second definition is it has really, really long tails, okay? Also, the vertices actually age. You get a sequence in time, which is projective, meaning that every graph along the sequence is a subset of the graph before. To model some real systems, you want that. To model other real systems, you don't want that, okay? If people are dropping out, you might want the first kind. If people are not dropping out, you probably want the second kind. Okay, and then if you're a statistician, you really care about the Aldous-Hoover theorem, and this gives you a generalization to sparse graphs. Okay, so can we get both? These both sound great, and the answer is no. The only cases on which these coincide are dense graphs. Okay? So these are really giving you two different sets of graphs. So the statisticians have told us they like the second one, but I'm like, okay, but you know, they're giving you two different sets. So, you know, if your graph happens to look like the ones that the rescaled graphs can go towards, those are the ones you want. If your real world graph is the other kind, then you want the stretched. And what sparsity can we achieve? And the only condition is that it has divergent average degree. Okay, so the average degree has to diverge, but other than that, I don't have to tell you what you know, function the density goes like as a function of n. It just has to go at least such that. So you know, it would be fine if I had n log n or even n, you know, a very small root of n larger. Okay, so now we've seen that given this thing, we can generate these functions, okay, which represent the limit of the graphs. But how does that help us think about, okay, so we can get these limiting functions. How does that help us generate a graph? We all know how using the Erdős-Rényi model to generate a graph. So how would these functions help us? Okay, well, the traditional model for dense graphs is the stochastic block model. Okay, so if people don't want just an Erdős-Rényi model with one density, they usually say, okay, I have k species of particles, okay, or k species of individuals on my social network, and within each type, there's a certain probability of connection, and between two different types, there's another probability of connection. If I have k types, I have k choose two probabilities of connection, okay? And they fit to that. And with, you know, real world networks, they used to also fit to that, okay? But the problem is that as your network, as n gets larger and larger, then you have to start letting k scale with n. You end up getting tons of parameters and you end up overfitting, okay? So there were non-parametric models, which people started looking at in 2002, actually, in which they said, okay, I'm just gonna generate features, okay? I'm gonna randomly generate some features, let's say in the interval 0, 1, and I'm gonna connect I and j with a so I'm gonna give you a function, and I'm gonna say I and j get connected with probability w of I and j. So I give you a function. Instead of giving you a block with k choose two parameters, I give you a function. So you might want some smoothness in that function or something. Okay, and you denote this resultant random graph by gn of w. It comes from that function w, okay? So how do we do this in more than just a way of saying, give me some w when I'm going to do this? So Bolobash and Reardon for bounded w, so think about the uniform attachment graph could have been described by a bounded w. If you have a feature space and a probability distribution over that feature space, so what I think is that, okay, I'm just going to, you know, generate people who have, you know, one of, I don't know, X could be a vector, okay? So X could describe several of your characteristics, and I generate individual after individual with, you know, height and weight and that kind of thing, and then I connect them with a probability in which I'm gonna, these are sparse ones though, so I'm gonna scale by rho n. So actually, Bolobash and Reardon did bounded W, which is a little more than dense. What it required is that different parts of the graph did not scale too differently, okay? And then we did something similar For unbounded W, so this generalizes sparse or de Shreny random graphs, which you get by taking P to be an inverse power of n. And this gives power law degree distributions. It's exchangeable but not projective. So as I said, as you go on in this sequence, one is not a subset of the previous one because I'm dividing through by the density, which is essentially like knocking out some of the previous edges. Okay, so that's one process, and that actually corresponds to that first rescaling. The one that corresponds to the stretching is a little weirder. This is done with Nina Holden. So what I'm going to do is I'm going to have a sigma finite measure space, okay? And I'm going to have a Poisson process of points with an intensity T mu, so in time it gets larger. And I'm going to generate these points, and then I'm going to connect, and so what these points are that I'm generating are features. And now these features can be unbounded. They can be wealth. They can be other things that we don't think of conventionally as bounded. I can say, you know, height is bounded because there's never been someone taller than 10 feet. But wealth is not naturally bounded in that way. And so I say, okay, someone of this wealth and that wealth and this height and that height and various other features connect to each other with some probability, okay? And so let's look at what happens. So I generate these features. Let me just think of it as one-dimensional for a moment. And then I take each of the 4 choose 2 pairs and I flip my weighted coin, weighted by W, and it turns out that 2 connects to both 3 and 4. 1 doesn't connect to anybody, so I don't show you one. I delete it. And I really have to think about deleting it because as time goes on, I've got these things further and further out. Okay, and then by time 2, what has happened is that, 7 came in and it connected to 1. And so now 1, which was just, 1 is, you know, Facebook just announced 2 billion people, okay? And there are, what, 6 or 7 billion people in the world. So you can think of the people who haven't been born, who've been born but haven't yet connected to anyone on Facebook. Those are like, that's like 1, but when 7 comes in, it connects to 1, okay? And so then 1 becomes real on Facebook. And so we go on. And just to give you a picture, this rescaled one tends to look like this. It contains power laws. And this stretched one with these unbounded features has even longer tails, okay? Okay, finally, does any of this make sense? I mean, I told you, this is the Facebook graph I'm talking about. Well, you know, is it actually a statistically consistent way of generating how this graph is going to look? And so the traditional approach, you know, if I have the graph today on n nodes and I want to predict a similar graph on 2 n nodes, the traditional approach way back when was to use a stochastic block model, one of these things with k species, to fit the k species to estimate those parameters, all the PIIs of connecting within my own species and the PIJs of connecting to other species, and then generate a new graph with those parameters. So the nonparametric approach says I'm going to give you, I'm going to model G as a W random graph, as the random graph I generate by flipping my coins with weight W of xi and xj. I'm going to estimate, learn an approximation W hat to W, and then I'm going to generate the new graph using W hat. So I take a measurement, I estimate this, and then using this, I flip my coins and I get out a model of a larger size. And so our task is to estimate an approximation from a single sample. Okay, and the proof is about 60 pages, but if W is in L2, if the density is going to 0, and if the average degree is blowing up, then yes, you can do this in a statistically consistent fashion. Doesn't mean you can do it computationally efficiently at all, okay? There are certainly going to be examples where you can't do it computationally efficiently. You know, if it's a strictly monotone degree sequence, then you can do it quickly, and there are some other conditions under which you can do it quickly. But I think it's a really interesting area. When can you do this computationally efficiently? Okay, private network estimation. Okay, so, you know, we know that it's, you know, difficult for information not to leak, even from a database, okay? This is particularly difficult for graphs because your connections reveal information. So, you know, in 2009, they looked at things like the Facebook graph and they said, oh, we can with high probability estimate your sexual orientation just by looking at who your friends are. And some of them may have announced their sexual orientations. And so we have a model and we, with high probability, can predict your sexual orientation, even if you have not revealed that information, okay? So it's not just the information you reveal about yourself, but the information your friends and contacts reveal that does this. And so naive anonymization can be undone. We need a more principled approach. So a few years ago with Adam Smith, who's one of the original differential privacy people, we looked at this question, and what you really want is no differential privacy. You want the probability of something happening if I am in the network or I'm not in the network to not be very different, okay, to be 1 plus or minus epsilon, and then it's epsilon no differentially private. There are other notions like edge differentially private, which are not nearly as strong. I really care about removing me from the network, not just removing an edge from the network. Okay, what I really care about is whether my information, and I'm a node, I'm not an edge, okay? And so most of the previous work involved either edge differential privacy or dense graphs. And so with Adam Smith, we looked at this question, and we weren't able to do it for W's and LP. We were able to do it for bounded W's, which are still a little bit more. They're like the things that Bolobosh and Reardon had looked at. It's more than dense graphs. And we were able to show that you can get node differential privacy. And we're looking at whether that can be extended, and we needed a degree that went up like at least log n, okay? Okay, so now we have this picture from a sequence of graphs. We can take their adjacency matrix and in various ways for dense and for sparse, get to a limit. If I just hand you this function, instead of handing you GNP with a constant p, I hand you a function, I can now really think about generating different kinds of graphs. And if you take a snapshot of a graph, you can get this function in a consistent way so that the estimate of it then allows you to generate realizations of that graph in a statistically consistent way. So what are some applications of this? Recently with Edo Araldi, who's at Harvard, and Christina Lee, who's a grad student just finishing here, we've done a couple, well, with Edo we did one. Both of them were with Christina Lee. So one thing we corrected for network effects, interference among nodes in A/B testing. Okay, if you try to do A/B testing on a network, you know, you can't do it like you do it for independent individuals, right? You can't say, oh, I'm gonna, be assigning flu shots. So Hervé, I say I give your wife or your partner a flu shot. I give maybe any kids in the home, a flu shot. I don't give you a flu shot. I see you don't get the flu, and I say, you see, whether or not I give you a flu shot, you still don't get the flu. Well, that's crazy, right? So anything for which the connections are relevant, any property that you mention for which the connections are relevant, you really need to do something totally different than the regular A/B testing. So with Graphons, we have a new process for doing that, which is about to be used by LinkedIn, which is great. And then a second application, the one I'll focus on here for my remaining 10, 15 minutes, is collaborative filtering and network completion, either to estimate recommendations on a sparse bipartite network like Netflix or Amazon, or, when I talked to Ali Taimur, he said, oh, yes, the development economists really care about filling in sparsely sampled communities in certain countries. Okay, so this is what we'll focus on. So we could either have, Netflix, Amazon, whatever, users and movies, or users and products, and how much they like them. So often we have a 5-star system. We could do it for social network completion, people to people. This is important, for example, if you're trying to suggest friends to somebody on a network, do you just want triangle completion, or should you be doing something more sophisticated than that? Or for weighted social network completion, so I don't have the same strength of connection to all the people I'm connected to on Facebook. There are some that I really like what they say. I see them, they put more of them in my feed, that kind of thing. Okay, so this is really a matrix completion problem. So let's say on one side, we have people, and there are characteristics of each of those people. So I might say, oh, your latent variable space is 100-dimensional when I'm connecting on Facebook. I don't know what the relevant properties are, but they're probably the latent variable space is probably pretty high. I mean, surely it has to do with, what universities you've gone to. It has to do with what interests you have. It has to do with a lot of different things, okay? Or if I'm talking about movies, there are lots of characteristics of movies, right? There's genre, there's awards, there's all kinds of things that I may not even realize are relevant latent variables there, okay? So I'm trying to do a matrix completion problem here. The Aldous-Hoover theorem for dense graphs, even though this graph is not dense, but what it tells us here is that our matrix, so the Aldous-Hoover theorem is a generalization of De Finetti's theorem for a sequence. And De Finetti's theorem tells us, it's how you get the polyurn, for those of you who know the polyurn. If I tell you the density, I can estimate things for you that you wouldn't think I could estimate, that you would think would have depended on which ball went into which bin at which time, okay? But it turns out the only thing that's relevant is the density. The Aldous-Hoover theorem is a 2-dimensional generalization, 2-dimensional dense generalization of that. What we did with Nina was a 2-dimensional sparse generalization. But even at the 2-dimensional dense generalization, what it tells us is that if I have only a single ergodic component, or I break things down by ergodic components, this thing only depends on the latent variables associated with the people, the latent variables associated with the movies, and some epsilon ij, which I could choose uniformly, randomly in 0, 1, which could be like my density in De Finetti's theorem or in the polyurn problem, okay? And so what that tells me is if I now take an expectation over these, so I've got that, okay? And I now take an expectation over those epsilons, and look what I have. I have a function which depends on the latent variables of the people, the latent variables of the movies. It's one of these W functions, right? It's one of these graphons, okay? And so what I'm gonna do is I'm gonna very sparsely sample this. I'll tell you in a little while how sparsely. But I'm gonna observe each entry independently with probability P. So I'm a development economist, and let's say it's people and people, and I very sparsely sample some of these and see who's connected to whom. And I want to try to fill it in, okay? And in general, if these were different, then they would each have their own D. If it is people and development economics, then God knows what the dimension of the space is. It can be pretty high, because I don't know what they're connecting on. But let's say that the latent variable space has that dimension. So here, if I'm talking about Netflix, all the relevant features of the person, okay, which would be relevant for choosing movies, and all the relevant features of the movies for making them choosable by people, okay? And so given the observed data matrix is very sparsely and possibly also noisily sampled matrix, can I get the expectation? This is what I would do if y was either 0 or 1 or y was in 0, 1. If I wanted to look at, 5 stars, okay, 1 up through 5 stars, then I could look at 5 different matrices. You either have a 1 or you don't have a 1. You either have a 2 or you don't have a 2. I could look at those and ask not just can I get the expectation, but can I get the whole distribution of the stars, okay, of the y's. And ideally, what I'd like to do, okay, is sample like 1 over n, which is like a constant degree, okay? That's how much I'd like to sample, so that I don't have to, talk to too many of the people in this community, or so that I don't have to, do I really have to have watched a number of movies that scales with n for you to be able to tell me what I'm gonna like? That's pretty bad. I don't watch that many movies, okay? So Chatterjee, a couple of years ago, had something which said that you could estimate if you sampled like, let's say if n is 50, if d is 50, n to the minus 1 over 25, I don't want to have had to have watched 25th root of n number of movies on Netflix, okay? Or rated n to the 125th number of products on Amazon, God forbid. I'd be broke, okay? So the challenge of sparsity is that if I look at these, there are no overlaps, okay? I just don't watch that many movies to overlap with Nicole, okay? So basically, we say they're similar if the neighbors are similar, right? If the neighbors' neighbors are similar. Okay, so Abe and Sandin had this wonderful work on stochastic block models in which they came up with an expanding neighborhood notion. So what they said is, let's go out from the movies to the people, to the movies, and on and on. And look, we've got overlap, okay? So by the birthday paradox, I want the boundary when I go out to be like square root of n. So instead of me having to watch all the movies, I'm gonna look at neighbors, 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 okay? And there's with good probability, there's gonna be overlap if that's of order square root of n. So that tells me how far I have to go out given how densely or sparsely I'm sampling. Okay, and then you compare products of ratings along the path and you treat these graphons as operators and you control the variance and everything. You go through all that. And what you get is you get this theorem which says that assuming W is Lipschitz, so W is the function which describes, given my attributes as a person and the movie's attributes as a movie, okay, given that that's Lipschitz and of rank D, the data points only have to be observed like D squared, which hopefully is not scaling with n, over n, okay? So I can do a constant number of, so I can have watched a constant number of movies, okay? And then the mean square error will go to 0. And in fact, if I do a little bit more than that, then with high probability, it'll go to 0. And this is much better than the Chatterjee result, which meant that I had to watch, you know, a root of n number of movies. So that's just an example of what you can do with this. So summary. Theory of graph convergence gives us a way to compare graphs of different sizes. We can do this for dense graphs and have all kinds of equivalences. Bounded degree graphs, there are only a few kinds of equivalences. What we really care about, sparse graphs of unbounded degree. The reason this really took a long time, this one, is because we had to get a new sparse Simoretti lemma, which really was very interesting in its own right, I think, and that was for the rescaled ones. And then these uniform tail regular ones were the kind where we stretched, where the features were unbounded. They provide models to generate random graphs. We can machine learn, we can estimate and predict these graphs. We can do it consistently for very general unbounded W's, and consistently and differentially privately for bounded W's. And then using Graphon methods, we can do a lot of different things. And I just gave you one example, which was how to complete a very sparsely, and it turns out also noisily, sampled network.